Welcome to an AP tutorial with Ms. Taylor. Today we're looking at empirical formulas with combustion analysis. We're going to start with a simple problem where we have burned a simple hydrocarbon that contains only carbon and hydrogen in excess oxygen. So the thing to keep in mind with combustion analysis is that all of the carbon from your compound is going to be captured in the form of carbon dioxide, and that all of the hydrogen from the compound is going to be caught in the water. So since this one's simple and only has carbon and hydrogen in it, I'm not going to go all the way through to grams. I'm going to stop at moles of carbon and moles of hydrogen. So we'll start with the carbon dioxide to get the moles of carbon. So we've got 0.845 grams of carbon dioxide. We're going to first convert that to moles. Molar mass of carbon dioxide is 44.01 grams. And once we've converted that to from grams to moles, I'm going to use a formula ratio, and that's what I call simply the ratio of moles in the formula itself. So for every 1 mole of carbon dioxide, you get 1 mole of carbon atoms. And that's going to give us 0.01920 moles of carbon. Alright, and let's take the water to get the hydrogen. So we're going from 0.173 grams H2O. Convert that to moles. And water's molar mass is 18.016. It's a handy one to have memorized. And then for every 1 mole of water, we get 2 moles of hydrogen from it. And that, interestingly enough, gives us 0.01920 moles of hydrogen. And so normally we would pick up and divide by the smallest number of moles, multiply till whole. But since it's obvious that we have equal number of moles of carbon and hydrogen in our compound, the empirical formula is CH. Now that was a really simple problem. Let's look at one that involves a tad more work. What if we burn a hydrocarbon that contains carbon, hydrogen, and oxygen? The key on a problem like this is, just like the other one, the carbon from the compound is captured in the form of carbon dioxide. The hydrogen is trapped in the water vapor, but we have to calculate the oxygen. And since there's 2 sources of oxygen, one being the compound we burned and the other being the O2 from the combustion process, we have to get the masses of carbon and hydrogen and then subtract that from the mass of our compound to get the grams of oxygen. And then from there it becomes a normal empirical formula problem. So let's look at this. I'm going to start with the grams of CO2 to get my to go all the way to grams of carbon. And in this one we have to go to grams because we have to have it in grams to subtract from the mass of our compound that we started with. So that molar mass, again, is 44.01. And for every 1 mole of carbon dioxide, we get 1 mole of carbon. And 1 mole of carbon has a mass of 12.01 grams. And so that is actually going to give us something that's going to round up to 0.1. grams of carbon. You should get 0.0999 something in your calculator and it'll round up. So there's the mass of carbon that was in our compound. Now we're going to use the mass of water vapor to get the mass of hydrogen that was in our compound. And molar mass of water is 18.016. And for every 1 mole of water, we get 2 moles of hydrogen. And 1 mole of hydrogen atoms has a tiny mass of 1.008 grams. Alright, and multiplying this, 0.15 times 2 times 1.008, get that answer, then divide that by 18.016. That is going to come out to be 0.0168 grams. I'm running out of space a little bit there. Okay, well now we've got to get the oxygen. We've got 0.2500 grams of compound that we know contains the 3 elements. So if we subtract the masses of 2 of the elements, we'll get the third one. So we're going to subtract the 0.1 grams of carbon and the 0.0168 grams of hydrogen. And that is going to give us 0.1332 grams of oxygen. So from here, we can carry this out like a normal empirical formula problem. And if you've been in my class, there's a poem that we use to remember the steps. Percent to gram, gram to mole, divide by smallest, multiply till whole. Well, in this case, we weren't given mass percent data, but we were able to find the masses in grams. So then our next step would be to take these masses in grams and convert those to moles. So I'm going to scoot this down a little bit. I'm going to switch colors. So for carbon, we had 0.1 grams, and we're going to use molar mass to convert that back to moles. And that's going to give us 0.008326 moles. Our hydrogen, we had 0.0168 grams. And we're going to divide that by 1.008. That's going to give us 0.01667 moles. And then finally the oxygen, we've got 0.1332 grams. And we're going to divide that by 16. And that's going to give us 0.008325 moles. Alright, so the next step would be to divide each one of these by the smallest number of moles. So the oxygen, by a tiny amount, is our smallest number of moles. 0.08325. And that's pretty much going to come out to be 1. Alright, this one in your calculator safely gives you 2, and then of course this last one is going to give us 1. So we got a nice set of whole numbers. So the empirical formula for this one is going to be CH2O. So again, the keys on this problem for combustion analysis is to remember where you're getting the masses of your individual elements. Carbon ends up in the carbon dioxide, hydrogen ends up in the water, and then if you have oxygen or some other element in your sample, you have to subtract the masses of the carbon and hydrogen from the mass of the compound to get the mass of the third element. And then you carry on as normal. So hopefully this helps you out. Have a good evening.